Storage, Part 2. In this nugget, we're going to be talking about storage. This is Part 2, where we'll start off with just a discussion of something called parallel ATA. This is because the data moves in parallel like on a multi-lane highway. We'll also take a look at hard drive components themselves, what a platter is, what the actuator arm is, some of those various kinds of things, as well as logical segments and logical storage areas on a hard drive. We'll take a look at hard drive installation, which is actually fairly simple, but I'll show you a simple example of how that can be done. By the way, installation and removal is pretty much the same thing, just in reverse. And then we'll also take a look here at storage controllers. The actual intelligence for a drive is normally found actually on the hard drive, but the controllers is an interface between the hard drive and the motherboard. And then we'll also take a look at drive interface standards, such as the various editions of ATAPI that you may have heard of, and serial ATA and the like. Alright, as we get started here talking about storage, we're going to start off first of all talking about parallel ATA configuration, or PATA as it's also known. And what we have with this is we don't have any kind of termination or device IDs involved in this. And I only bring that up because later on we'll talk about SCSI, where you'll see that it does require both termination and a device ID. And this helps to identify the device on a SCSI chain, as well as to help prevent signal bounce. And that's just to make sure that the devices are properly operating. But we'll talk about that again when we talk about SCSI. But one of the other things you'll want to know about as it relates to parallel ATA is that there's a few different positions that you can put the drives on. And those are going to be in these three positions: master, slave, or cable select. And I'll show you that here in a moment, both on the drive and on the cable, by way of photographs. And then also bear in mind that a parallel ATA cable, its maximum specification is supposed to be only up to 18 inches, although I've seen some longer. I've seen some 24 inches, for example. And they are going to be 80 wire cables. Okay, so there's 80 little wires inside of that cable. Only 40 of those wires are actually used for any kind of transmission, though, and it's a 40-pin cable. So what's the other 40 pins? What's the other 40 pins in this 80 wire cable supposed to be for? Well, those are for shielding, which gives a better signal integrity on that cable. And we'll see that also in a PDF file that I'll talk about here. Because of the fact that they added an additional 40 wires for insulation and shielding, it gives it better signal integrity, and eventually it also helps to contribute to a better data throughput. Now, the cable I was talking about, we show here as by way of example. This is a round cable, although most of them are probably actually going to be flat ribbon cables, which have a tendency to block airflow and are difficult to work with. That's why some manufacturers came up with a round design here, which they also have given additional shielding. If I kind of zoom in here, I think you can see that there's kind of a braided shielding that goes around that, which helps to mitigate the crosstalk that the 80 wire design is meant to help with. Okay. Also, you'll see that there's one end of this which is designated as system. This would connect to the motherboard or the interface for the connector card or the adapter card where you would plug this in. Normally that's going to be on a motherboard, though. And then the other two ends, notice they're on a shorter connection right down here. Notice the length of this cable compared to this length of cable. Well, the ones that are connected on the shorter ends of this would be where the actual drives would connect. If you have a single drive, normally that's going to be put in the master position that you see here. If you have two drives, one goes on master, one goes on slave. If you connect the drives, then there will be also jumper positions on the drives themselves where you can specify them as cable select or master or slave, and we'll take a look at that here in a moment. But before we do that, though, I just took the end of that same cable that we were just now looking at. This is the system end of it. And you can see, if you want to count them all up there, there are indeed 40 pin positions there. But if you were to look at these colored wires here, there's actually 80 wires there. The white ones are actually the ones that are designed to help protect from crosstalk. And then the other end of the cable, where you actually connect it to the drive, would go on these 40 pins that we see over here. If I can't seem to get my pen working, there we go. These 40 pins that we see over here on the side. And you can see also there's a pin missing here, which corresponds to the blank that was in the actual connector itself. And then there's also a keyed section right up here at the top, which corresponds to the keyed section on the actual cable itself as well. And you can kind of see there's a key portion there. Also, as we move our way over to the right, you'll notice that there's a jumper block right here. And this is where you would move this white jumper left or right to designate whether it's cable select, master, whether it's slave, and so forth. Generally speaking, I use only cable select, and that usually works pretty well. Some older systems, however, might require you to specify master or slave, literally, rather than to use a cable select setting. And then this is where our power connection would go, and there's a 4-pin power connection. And that would be what we call a Molex connector. And then having tipped the drive up, we can see here that I've now, looking at a different perspective of it, we're looking at the printed circuit board side of this, and there's a couple of different places where it will identify whether or not you want to use cable select, master, or slave. Right now, the jumper appears across these first 2 pins, so it's set at cable select, which you can see there, as well as here on the printed circuit board. If I were to move it over one, it would be in the slave position, and if I were to move it over, one more, which would be right here, then that would be the master position. Okay, so that would be at the end of the cable, and of course the slave would be if it were the middle, middle connector on the drive. Okay, on the drive cable. Also, there's a couple of other pin settings here. What in the world are these for? Well, these can be generally used for manufacturer-specific purposes or proprietary purposes. Maybe a manufacturer's configured a drive with a certain settings for just their computers, and that's kind of what those are for. But for A+ exam purposes, we're concerned about cable select, slave, and master positions. And then here we've just got a photograph of a laptop hard drive. Now, in terms of the standards and everything like that, the laptop and the desktop hard drives are going to be relatively the same. I'll show you any of the differences. But otherwise, we're going to really consider them to be the same in terms of the standards themselves. One of the things that we will see that's different is a laptop hard drive is going to be let me see if I can write this, 2.5 inches, and that's not literally 2.5 inches from one edge of the casing to the other. There's actually a little bit of clearance involved in that as well. This refers to the actual round platters themselves inside of the hard drives. Those are 2.5 inches, whereas a desktop PC, I'll put desktop PC hard drive, would be 3.5 inches. Okay, so there's a little bit of difference in size right there. Also, the connectors themselves here as well, connectors themselves here as well are going to be different on a laptop, because you'll see that these are going to be cropped a little bit closer together. You can't take a desktop connector and fit them on there. It'll be too wide, but they're specially designated and sized for a connector inside of a laptop. Also, this is an IDE drive, also known as a parallel ATA drive. We can consider those synonymous for our discussion. And this is going to use that 40-pin design, again, even though they're sized a little bit differently. Nowadays, however, you're going to see for most desktop as well as laptop computers that are relatively new, they're going to go to the serial ATA design as well, which is much simpler, but also much better. Now, I took a photograph of this particular hard drive, and that's what I'm going to demonstrate a lot of our things with here, because this one was a bad hard drive. So I used my Torx screws and all of that, and you can kind of, if I zoom in here, you'll see that some of these screws are going to be just normal Phillips head, but as soon as I remove this printed circuit board, then underneath that, they're all Torx screws. And so in order to dismantle this, that's what I kind of had to use there. Also, I'd like to point out here that when we talk about the drive controller, this printed circuit board we see here has most of the intelligence for handling this hard drive and the signaling and all of that kind of stuff, the data throughput and the like. The controllers that we use on motherboards or on dedicated expansion cards for hard drives, those are normally just going to be interface items. It just kind of handles the traffic, and it's a little oversimplifying it here, but the actual intelligence resides, for the most part, on this printed circuit board. Now, one of the things that you will see here on the drive is it'll probably have some kind of a warning here that you should not break the seal. This is actually just a sticker that appears over an opening, and I'll actually remove that sticker in a moment so I can show you. But the reason why you should not mess with this sticker is because if you remove it, then it could allow dust and other contaminants to get inside of the hard drive and affect the performance or reliability, more likely, of this drive. And then here's where I just removed that sticker, and you can see that there is an opening in this that would otherwise expose that drive. You don't normally want to remove that. And in case you're wondering why in the world that thing's there in the first place, it's because when the sticker is covering it up, it helps to equalize the pressure inside the drive with whatever's in the atmosphere. So, for example, if you're, in a high altitude place like Denver, the Mile High City, then it would allow air to kind of move in and out of that gradually, just a little bit, but without allowing contaminants inside of it. So there has to be some kind of equalization there for the drive. Whereas if you were at sea level, then of course that would be a little bit different. Alright, and then here I just took the controller off of the hard drive. I just used the Phillips head screwdriver to remove those Phillips head screws. Actually, it had to be a jeweler's screwdriver because they were kind of small screws. Anyway, you can see here that this is the casing, and this is actually the controller that appears here. And then we also have a couple of other things to show you here, such as this photograph, where I have taken off the housing, the casing on the outside there, used my Torx screwdriver to remove this item. And if we kind of zoom in here, you can see that there's a gasket to seal out dust and other contaminants from the hard drive. And then on the inside, we can see quite a lot more detail. And you can see that even just taking the casing off there, we get some dust contaminants on the surface of this platter. That or my house is just really dusty. And then having zoomed in a little further here, we see some additional detail. Now, you don't need to memorize any of this for the A+ exam, but since most of the time you don't crack open hard drive cases, I just wanted to show you some detail about all of this. The key thing here is the platters, and you can see that they're very shiny, reflective kinds of platters. In fact, let me push in a little further here. You can even see that the reflection of this actuator arm appears just pretty much in a perfect mirrored format on the surface of this platter. And then what you'll also see here is the actual head itself. This is a magnetic head which reads and writes magnetic signals or data to the surface of this platter. It's a metal platter with a magnetic coating on it, and it's kind of amazing how these things work. I remember years ago I saw a demonstration, I think it was from Western Digital, where they had the case of the hard drive was actually an acrylic case, and they showed this whole thing just in operation, and this thing just moves extremely fast all the way across these platters. Also, by the way, this arm right here is called the actuator arm, and then the mechanics that actually control the function and the movement of all of this is inside of this more centrally located position in here. And that's where it controls, where to actually put those heads. Notice that there's also multiple platters, and each one of these actuators will have a head on it, and there will be one under here which will actually read both sides of this platter. So this actuator arm, let me actually pushed in a little too far here, so let me come back out. You'll see that this actuator arm here will have one head on it, but this one under here will actually have a head that reads the underside of the top platter and the top side of the second platter that we have down here. So it's able to maximize the surface area. And then just for a little further enlightenment, let's go ahead and push in. I'm zooming in now using Photoshop at 100% magnification on the head at the end of the actuator arm. And you can see it right here. It's actually in contact with the surface of this platter. Now, one thing to keep in mind with this as well, and this is something we don't have to worry about anymore, but these heads are automatically parked. Back in the old days, you had to be really concerned about heads that were self-parking or not self-parking, because when the drive spins down and it's no longer moving, you want this to it actually rests on top of this media. And that sounds kind of risky, but that's actually okay. But in the old days, they might not have been self-parking, and so then they would kind of hover just slightly above the platter in the magnetic media, and if there was a slight jolt or anything to this, that it could have come in contact with this in an abrupt way and potentially damaged that magnetic media. The old hard drives from way back when, decades ago, were extremely sensitive to any kind of vibration or movement, and they went bad pretty often. But now, even though hard drives will still go bad from time to time, they are much more durable and rugged than they were back in the early days. And then we also will take another look at this hard drive, and one thing I want to point out is in the corner of this, and this is not an A+ exam item, but just so you know, as the hard drive spins around at either 5,400, 7,200, or 10,000 RPMs, it generates its own wind, and the hope is that it'll cast off any contaminants or particulates that may have rested on the platter here or somehow gotten inside of the hard drive. and will get caught on this kind of cloth-like material back here. Notice that as the wind comes around, there's a grooved area here where hopefully it'll get cast off and then get trapped back in here or get trapped by this cloth-like material there. And then you can also see from this this kind of shocking-looking picture here with this creepy-looking guy looking onto the surface of this platter that it definitely is an actual mirror-like finish. In fact, if I push in here, you can see quite a lot of detail, probably more detail than you'd ever want to see. I think I finally have an explanation for why this particular guy never got a lot of dates in college. Anyway, that's the mirror-like surface of this these particular platters. I just found that kind of novel. Now, I've already talked about a lot of the various hard drive components here as we were taking a look at the pictures and things here just a moment ago. But let's do review a couple of these, and then we'll look at some new concepts here as well. The first thing there is the platter. Remember, that's that shiny surface that we looked at there. It's got some, it's actually made of metal. It has a magnetic coating on it. It also, by the way, has some protective properties that are added to it as well to protect it against its own read-write heads when they do come into contact with that platter. Sometimes that happens accidentally. I mentioned earlier that they're supposed to park and contact in what we call a contact start-stop design or a CSS design. But sometimes they may, through shock, for example, especially if it's a laptop hard drive, through shock, the heads may accidentally crash onto the platters when they're not supposed to. Because during normal operation, when they're spinning around, a thin cushion of air is created underneath the heads, and it keeps them hovering over the top of those hard drive platters. But if it accidentally contacts it, then it could ruin some data or damage the hard drive. So anyway, there's some protective properties there on the actual platter that protects it against that kind of thing. And then as we move along here, we see a few other terms, and these are things that you cannot see just by looking at a physical picture of the hard drive. These are all kind of logical items that are put there mostly by low-level formatting, which is done at the factory. One of the first ones I want to look at here, and I'm kind of going out of order, is a track. And for that, I need to go ahead and draw just a circle of a platter here. And you know that these things will actually have concentric circles on them. These are logical markings that are put on there at the factory. And these look more like concentric ovals, and I apologize for that, but I cannot seem to draw a very good circle. Anyway, these are actually tracks, as you would imagine. They go around here. Each one of these are numbered differently and uniquely. But the thing is, you can't use only tracks to store data, because if I had let's say a 1 kilobyte file, and I needed to store it here, well, with only tracks, I'd have to store that 1K file here in this whole track, and it would waste all the additional space for all these megabytes that this track could have occupied. Okay, so now I have to dedicate it to that 1K file. So what we do in order to mitigate that is we divide these tracks into, you guessed it, sectors. Okay, so the concentric circle itself is a track, and then the divisions within that are called the sectors. Now, where in the world, then, does this cylinder concept come into play? That's actually kind of related to track. You see, remember, we'll have multiple platters inside of the hard drive, usually 3 or 4, sometimes as many as a dozen different platters. Well, this outside, track here, for example, it's actually duplicated on the underside of this same platter, and it's also on all of the other platters. They all have the exact same measurement for a track that appears right here. Collectively, let's say we have 3 platters. Collectively, this outside track on all 3 platters is known as the cylinder. So that's what that refers to there. And then the actual cluster, what that is when you format this, then it can be divided up into partitions. And I can't really draw enough additional lines on here to, I think, illustrate that well. But the operating system that you use, for example, Windows, when you format a hard drive within Windows, you can divide this up into multiple partitions. I might have a C drive on here, a C partition, a D partition, or maybe others as well. And as I partition this out, it will then have discrete units of storage on here known as clusters. And these clusters will be the smallest amount of storage available. Kind of subsections, if you will, if you want to think of it conceptually at least, subsections of a sector. And then we also have controllers. Remember, the controller, in literal terms at least, is actually on the actual hard drive itself. It's the printed circuit board. And then when you actually put it inside of the computer, you connect it to a host adapter. This can be an expansion card that you put in for serial ATA or IDE or enhanced IDE, or it could be a SCSI host adapter. So, and remember, the drive itself has the printed circuit board with most of the intelligence. The host adapter is mostly an interface to connect the drive to the rest of the system. Now we're going to continue our discussion of hard drives, including moving on to serial ATA as well. But one thing I want to show you here is just the basic installation of these hard drives. This is going to be really pretty simple, and it's going to be the same whether or not it's a serial ATA or an enhanced IDE, at least in terms of putting it inside of the case. So what we have here is a hard drive that goes into an internal drive bay, meaning that there's no access to this from the outside once the cover is put onto the computer case. This particular one, and they're all different, by the way. There's a lot of different ways of getting these. Some of them will have a little handle on it so that you can pull these out, and they might be hot swappable if they're SCSI, for example, or with some serial ATAs they may also be hot swappable. IDE or enhanced IDE rarely, if ever, is hot swappable. In fact, by design, it's really not. So anyway, but you'll have a case that goes here, or rather a cage that these drives go into, but they also have to go onto a rail, and that's what this is over here on the side. This is a drive rail. In this particular design, I think I have another picture of it. Let me show you this one. This is a toolless design. There it is. So you don't actually have to use any screws in this. This is just kind of a metal head on this side of it with a rubber grommet. This also helps to absorb vibration. And then on the other end of this is just a pin that goes into the screw hole on the drive. And then it just kind of holds it in like that. It just uses mostly just tension to hold it in. Now once you've got that these rails attached to the drive, that's when you will then go ahead and plug in the power in the back over here. There's the power and the serial ATA connectors in this particular case. And I've plugged those into the appropriate connectors on the drive, and then I just push this in, and then when it goes into place, you can see over here, I think we can zoom in, that there's a little tabbed section here. It's like a little groove. That goes behind this bevel on the hard drive cage, and then on the other end of the same device, this I push in on this, and then you can see it locks into place like these are over here on the side. These are now locked and snapped into place. In order to remove the drive, I would then just pull back on this tab and then pull this whole thing out again, and that's how that's basically done. Oh, by the way, this is not really an A+ exam objective item, but notice that I mark some of these by numbers. If you're using a RAID system, sometimes it's important to keep track of which drive is on which interface, and this is on the first, or actually the second interface, because it uses ordinal numbering. The first drive on the second interface, okay? And you can see down here it's a little bit out of focus, but this is on the first interface using ordinal number. That would be interface 0, and it's the first drive on interface 0. Okay, you don't have to memorize that, like I say, but it is useful sometimes if you have multiple drives and you need to keep track of which one's attached to which interface. Now earlier we looked at the back of an IDE drive, or more particularly its enhanced IDE, or EIDE, and this is very similar to that. In fact, the dimensions should be exactly the same from top to bottom and left to right here. However, what you'll see different though is the drive electronics and the actual controller that we see here. So this is the one of the connectors that you'll see here. This is for the power of a serial ATA connector. Notice that it's L-shaped. That helps to prevent you from plugging in the power, upside down or backwards or something like that, because it can only go in one way. Likewise, the data cable, which is a 7-wire data cable, plugs in here. It's also on an L shape. So that will help to assist in that. And then you'll also have here possibly other jumpers. We don't really normally use those for serial ATA. We don't really need to. Serial ATA is smart enough on its own to know what position a drive is in. Plus, it's a point-to-point connector. With serial ATA, you have one cable with a connector on both ends. So one end goes into the controller on the motherboard, for example, and the other end just goes into, into here on the hard drive, and you don't have a master-slave configuration or anything like that. So that's not really an issue at all there. And then in this particular hard drive, this one is a kind of a transitional hard drive, which allows you to use the older power style connector here if that's all your if that's all your power supply has. Okay. Or alternatively, if your computer has serial ATA power connectors, then you can use those either one. Just don't use both of them. For goodness sakes, don't use both of those. You'll probably burn something up. But one of the advantages of serial ATA is that these connectors are much friendlier in terms of the form factor. So this is very thin, and it can be a relatively long cable. In fact, it can be a meter long, whereas enhanced IDE is limited to only 18 inches. So it's, what's a meter? A little over 39 inches. So it could be potentially long. It also doesn't require a lot of width, like a ribbon cable does, so it doesn't block airflow very much either. And then the power connector here is actually fairly close to the same width as that we would have for a Molex connector, but I do find that they're still easier to plug in and unplug. In fact, in some ways, they're a little bit too easy. I find that serial ATA connectors and power connectors very often come unplugged or get jostled loose or something like that, but some serial ATA data cables also have a little interlock on them where it will snap into place, and you have to push down on them using your thumb to disengage them and then remove them. But otherwise, most of them have no such locking capability. Now, I told you earlier that most of the drive intelligence is actually found on the printed circuit board of the hard drive itself, but for the A+ exam objective purposes, they call the storage controller whatever's on, the motherboard, for example. So, integrated into the motherboard, and we saw pictures of this a few videos back. In one of my machines, I have 6 serial ATA connectors that are integrated into the motherboard that I can use. In this particular case, they could each be used as for separate drive connections for anything from CD and DVD or some kind of optical storage to internal hard drives as well, and I can use those separately, or I can have multiple hard drives put together in a RAID configuration, which we'll also talk about a little bit later on. The same kind of configuration could also be used, of course, in a RAID card. And with a RAID card, you can either decide to use RAID as a technology, or you can normally also decide to use each drive independently. In order to access the RAID properties, either of a motherboard integrated or a RAID card, either one, there's going to be a message during boot up that will tell you to press a key combination. Very often with RAID cards, I think from Adaptec, it's Control-A or Control-S, and then that will bring you into the BIOS for that RAID card. That's where you will then tell it what members of the RAID array to make part of the RAID array. And what kind of RAID technology you want to use, which we'll look at more specifically here shortly. And then we'll also have external serial ATA cards that you can also use. I'm using that actually on my server right now, where it plugs into one of the serial ATA connectors on the motherboard or somewhere else inside of the computer, and then it goes to a bracket that makes an external connection for an external serial ATA that I can use for external drives, for example. And then I got ahead of myself a little bit there, but again, to access the interface, you might have to press Control-A, Control-S, whatever message you see during boot up time. It should tell you what you need to do to get access to the storage controller's BIOS. Now, I'm going to again talk to you more about RAID and the configuration of RAID here at a later point in time, but for the time being also, I wanted to emphasize the interface for some of these items. This is where, if you had an external serial ATA controller, that this would connect to an internal connector, for example, on the motherboard, and then this would be the external connector here. It's a different form factor and everything, a different kind of cable that is used to connect to this. Then I could use my external serial ATA drive. And then here are the internal connectors. Again, the external serial ATA connector might plug into one of these, and otherwise I might have multiple hard drives plugged into these different ones. And on this particular motherboard, there's these 6, and then there's several others in different locations on the motherboard as well. These could be used for hard drives or optical drives, of course. And then we've seen this photograph here as well before, but just by way of quick review, since we're talking about these host adapters, this would be a device. It's a PCI Express device, which would add an additional serial ATA connector here. So, for example, if I'd run out of internal serial ATA connectors and I needed another one, well, this would provide that. And then on the other end of this would be an external serial ATA connector here. So I actually have 2, one internal and one external on this particular host adapter. And then we'd also talked about accessing the interface. Remember I mentioned earlier that in the startup of the computer, you'll see the BIOS message here. They need to press Control-I in this particular example to access the interface for the BIOS for this RAID. And then once you'd press Control-I, it would bring you into this. And you can see here that you could then do a number of things. You could create a RAID volume if you didn't already have one. You could delete a RAID volume if you wanted to start from scratch, for example. And a number of other options, which are pretty easy to figure out from this interface. And then when it comes to laptops for both serial ATA and IDE drives, the installation is mostly the same. And this may vary from one laptop to the next, but as a general rule, what we can see happening here is there's a particular location where the hard drive goes. On the other side of this hard drive right here is the actual case that this is screwed onto. You can see here that there's a white portion there where there's a screw hole, and that would then screw into this section right here, which you can see is cracked over here. Apparently, I've abused this laptop quite a bit. Anyway, what happened there is you would then just slide this out. Over here would be where all of the connectors are. In this case, it's an IDE laptop hard drive, and it makes the connection right there, and I'll show you that as well in a couple of other locations. So, for example, if we take a look at that same laptop in a different view, here you can see is the IDE connector for the 40 pins. The pins are on the hard drive, and then this is the female side of that on the actual laptop itself. If we look at the end of the hard drive from this laptop, I think I can get the picture right here. There it is. Then we can see the pins right there. Okay, and then you just slide it in basically, and then you tighten the screw down from the external side of the case, and you're pretty much done with the installation. For serial ATA, you pretty much do the same physical act in terms of installing the drive, just the connections are different, and you don't really have to worry about doing anything upside down or backwards because it only goes one direction anyway. Now, I've kind of alluded to serial ATA and integrated drive electronics or enhanced integrated drive electronics and so forth. Generally speaking, enhanced integrated drive electronics, or EIDE, and IDE, we pretty well consider synonymous, although enhanced IDE is more recent than just plain old IDE. IDE is an integrated drive electronics. ATA is the other part of the standard, and that's AT attachment. And then you'll see other acronyms down here, such as the AT, and this is the AT attachment packet interface, if you need to know what the acronym means. I don't know why that slipped up there. Anyway, let me go back to here. AT attachment packet interface. And then you see a number of other terms, Ultra ATA, DMA, and so forth. Let me explain a little bit about what this is all about and where we're going within this. First of all, this whole top part of this, you really don't have to be too concerned about any of these top parts that I've highlighted. The reason why is that for A+ exam objectives, they're considering current versions of Windows, such as Windows XP and later. Windows XP would be require too much overhead to even install on a system old enough so that this was its highest standard. Okay, all this stuff is pretty well antiquated and obsolete, and you only find it on really old computers in the junk heap, so to speak. These other ones are going to be more recent, although we're still going back several years if we're going to go to ATAPI 5. But with these, you can see that there's a speed increase as we move on up through the standards. Also, I want to point out that you see these acronyms change. We had Integrated Drive Electronics, AT Attachment, and then we went to ATAPI. What's going on here is it kind of settled on ATAPI as the official name, but before the actual standard of ATAPI 4, in this case, was actually introduced, the standard was kind of in beta, so to speak, or in testing phases, or the standard was actually written, but it was not officially ratified yet. So these drive manufacturers said, hey, we want to have all the features of ATAPI 4, but we can't put that on the box for the drives that we're trying to sell because it's not officially ratified yet. So they came up with their own terms instead. We'll just call it Ultra ATA or Fast ATA2 or Ultra DMA. You know, all these kinds of things that their own marketing names, or their own marketing people came up with. So that's why for the same standard, you might see several different ways to describe it. It does get a little bit confusing. But you can see, for example, with ATAPI 4 that it gives us a speed of 33 megabytes per second. Notice the uppercase B. And this is where we introduced the 80 conductor cable. From that point forward with IDE types of electronics, which is what ATAPI follows, then you can see that it increased the speed as it went down through. These are just technological changes that went through and made this better. Also, the 80 conductor cable down through these two standards was optional but recommended. Here, the 80 conductor cable, as you can see, became required starting with ATAPI 6. And then when we moved into ATAPI 7, you can see here as well, we got a higher speed, and this was where serial ATA was introduced as well. Although I will have to also point out that with serial ATA as the official standard, it is capable of 150 megabytes per second, whereas ATAPI 7 is capable of 133 megabytes per second. In fact, I'll change that on the official document that I upload. It'll say 150 for serial ATA. And then you can see over here to the right some more detail about that as well. ATAPI 8 is serial ATA 2. 300 megabits per second using the same 7-pin serial ATA cable. And then serial ATA 3, which just came out recently here, is now capable of 600 megabytes per second. And then just so that this wouldn't fall by the wayside, I went ahead and changed this online here so that you can see that this does have the correct information. 150 megabytes per second for serial ATA. Also, anything that does not say serial ATA on this chart refers to also another standard called parallel ATA, which I've already referenced many times before. The parallel ATA is what really describes that whole master-slave and cable select configuration. And it's called parallel, by the way, because the data travels in kind of parallel lanes to and from the hard drive, whereas serial ATA is more in a single file line, and that's why that works out. Parallel ATA also is what does not require termination and does not have device IDs. And then in terms of studying purposes as well, the other thing I would look at here that this Ultra DMA 66, which is actually part of the ATAPI 5 standard. I can't seem to get my mouse to work. There we go. That's what gives you 66 megabits per second. Okay, so that's why it's known as Ultra DMA 66. 66 megabits per second. Most of these do correlate that way. And then with this one, we also get 80 conductor cables if we want it, because this still applies down here. This all gets inherited by succeeding generations. The other thing to keep in mind with that as well is that in order to use whichever version of Ultra DMA you're interested in using, or ATAPI that you're interested in using, it has to also have support from the operating system, the BIOS, and the controller. That's usually not a problem with any modern computer, though. But again, at least starting with this edition here, that's what the A+ exam will be interested in, knowing that you can have the 80 conductor cable, the operating system must support it, the BIOS must support it, and the controller must support whichever version of this that you want to use. In this nugget, we talked about storage. And this was part 2, where we started off by talking about parallel ATA. Remember, that's also where you'll see things such as cable select, or master, or slave, all those sorts of things that you use normally an 80-wire cable to make a connection. That's what part of parallel ATA is. Then we took a look also at hard drive components. This could be things that you can't see with the naked eye, such as sectors and tracks and cylinders, but also some of the things you can, such as the platters themselves, the drive actuator arm, the actuator, the head. All those sorts of things are also things that we took a look at. We looked at hard drive installation, which is really pretty simple. You simply put screws on the side to put the rails on. In the case that I showed you, it was a screw-less design where you just slip on the rails, and it was pretty simple. Then you just lock it into place. The uninstallation, or the removal of it, is just the same thing in reverse. And then we took a look also at storage controllers. Remember, storage controllers is really not where the intelligence of the drive is. That's normally integrated onto the printed circuit board, but the storage controllers will provide the interface between the actual drive itself and the motherboard and the rest of the system. And we took a look also here at some drive interface standards, such as ATAPI and the various versions of that, what Ultra DMA means, and all of these sorts of things. Including, and more importantly, I think now and for the future, serial ATA standards. Well, I hope this has been informative for you, and I'd like to thank you for viewing.